Hi everyone, I'm Adrienne Sturgeon and I really appreciate you being here today. I put together this presentation to walk you through the security policy that was created specifically for the Green Pace organization. It's part of my work in Secure Coding course at SNHU, and I'll be highlighting the key components that help make a security policy truly effective. This security policy for GreenPace lays out the core standards and practices that help keep the organization's data and applications safe. It serves as a starting point for a broader defense in-depth approach. Alongside it, there's a graphic that breaks down this strategy and shows the different areas and layers that need to be protected. The threat matrix gives a clear picture of the types of security risks this policy is meant to handle. In the lower left corner, you'll find the threats that are both low in severity and unlikely to happen. As you move up the matrix, it shows risks that are more likely to occur, though they're still not very severe. On the lower right, it calls attention to threats that probably won't happen but could have serious consequences if they did. The top right highlights the ones that are both highly severe and very likely. Tools like CPP Check, which perform automated static analysis, help spot these kinds of threats early so they can be addressed before they become real problems. This security policy has 10 main principles. Validate input data. This practice ties into coding standards 4 and 9 and reminds us that data coming into the system needs to be checked thoroughly so it doesn't become a security liability. Heed compiler warnings. Compiler messages shouldn't be ignored because they can point to potential issues. This principle connects with coding standards 1, 2, 9, and 10, since fixing these warnings often aligns directly with best practices. Architect and design for security policies. This concept is backed by coding standards 6, 7, 8, and 10. It encourages developers to build security considerations right into the design phase rather than tracking them later on. Keep it simple. Simplicity makes code easier to maintain and harder to break, so this principle supports coding standards 2, 4, and 8 by reducing unnecessary complexity that can introduce vulnerabilities. Default deny. Instead of automatically granting access, it's safer to block all permissions at first and then allow only what's absolutely necessary. This ensures new users don't get more access than they need. Adhere to the principles of least privilege. Everyone should only be able to access what they actually need to do their job and nothing more, which helps keep sensitive data secure and systems protected from accidental misuse. Sanitize data sent to other systems. Clean input going out is just important as clean input coming in. This principle connects with Coding Standards 9 and emphasizes the preventing issues like injection attacks and data leaks. Practice defense in depth. This is about having multiple layers of security instead of relying on just one. It supports Coding Standard 5 and makes systems harder to compromise all at once. Use effective quality assurance techniques. Testing and review processes fall under this principle, which ties into Standards 3, 5, and 7. It helps catch issues early and keeps code quality high. Adopt a secure coding standard. Finally, following a clear and consistent set of coding guidelines like those in Standards 3 and 8 helps teams avoid common security pitfalls and write stronger, safer code from the start. The security policy lays out 10 essential coding standards, each ranked based on the level of risk shown in the threat matrix. 1. Don't add constant or volatile to reference types unnecessarily since it can lead to confusion and misuse in the code base. 2. Ensure functions that are supposed to return a value always do so on every possible path to maintain consistent behavior and prevent runtime errors. 3. Check the range before accessing elements in a structure to prevent out-of-bounds errors that could crash the program or open up security flaws. 4. Make sure the data is sanitized before passing it to complex subsystems so that any untrusted input data doesn't cause unexpected behavior or vulnerabilities. 5. Always release dynamically allocated resources properly to avoid memory leaks and potential system instability. 6. Understand what happens when you use assert or abort functions because these functions can end your program abruptly, and that might not be what you want. 7. Catch and handle all exceptions effectively rather than letting errors slip through and cause unpredictable outcomes. 8. Avoid making changes to standard namespaces so that you don't unintentionally introduce conflicts or make maintenance harder down the road. 9. Take care to maintain or make sure that system library functions don't cause overflows, which can silently lead to dangerous bugs or data corruption. 10. Write construction member initializers in the canonical order to avoid compiler warnings and to keep things orderly and predictable. Encryption at rest means data is protected while it's sitting in storage. That way, even if someone gets unauthorized access, they won't be able to read the data without the right decryption key. Putting this policy in place is critical because it helps guard sensitive information in the event of a breach. Encryption in transit comes into play when data is moving from one place to another. This form of encryption keeps data secure as it travels, and if someone tries to intercept it, they still won't be able to read it without the proper key. Encryption in use is about protecting data while it's actively being worked on. This adds an extra layer of defense, making sure information stays secure even while it's being processed or altered. Since encryption at rest and in transit already helps reduce risk, any unprotected data in use becomes a potential weak spot. That's why it's so important to develop techniques that allow data to remain encrypted even during use. It's a key part of building strong, full spectrum security. Authentication is how we confirm that someone is really who they say they are. It usually happens when new users are added or when someone logs in. This part of the policy makes sure that only approved individuals can get into the system or use its component by checking things like usernames and passwords. Authorization comes right after authentication and decides what someone is actually allowed to do once they're in. It defines each user's access level and it ensures people can't reach part of the system they shouldn't, which helps keep everything more secure. Accounting is all about keeping a record of what users do, whether they're updating databases, opening files, or making other changes. This kind of tracking is critical for staying on top of system activity. If something starts acting strangely, you can turn to these logs to figure out what went wrong and how to fix it. Next, I am presenting a variety of unit tests which provide varying results based on G-test framework. On this slide, I introduce a test that checks whether the collection starts off empty, which confirms the initial state behaves as expected. This slide shows a test verifying smart pointers do not have a null value. Then I tested the add entries method to make sure that adding a single item to an empty collection worked correctly. After that, I tested adding 5 different values to ensure the method handled multiple entries reliably. I followed up by checking whether the collection's maximum size updated appropriately as new entries were added. I also verified that the capacity increased in line with the collection's growth, which showed the storage adjustments were working. Next, I ran a test that resizes the collection to see if it performs as expected when adjusting to a new size. I continued by testing a scenario where the collection size decreases during a resize operation, and I confirmed it responded correctly. I also checked what happens when the collection is resized down to 0, and this worked the way it should. Then I tested the clearing functionality to confirm that it wiped all elements from the collection as intended. I also made sure that erasing the collection behaved consistently, clearing the data in a clean and reliable way. After that, I tested the reserve method. I confirmed that it can increase the collection's capacity while leaving its size unchanged if no new entries are added. I wanted to make sure that trying to access elements outside of the valid index range triggered out-of-range exceptions, and this worked as expected. I followed up by testing the assignment of values to the collection and everything behaved as it should. Finally, I double-checked that calling reserve still only increases capacity without affecting the collection's current size. The DevSecOps pipeline diagram shows the steps involved in building a secure application. Along this path, there are many opportunities to use automation to strengthen security, especially in the middle of the pipeline where a lot of powerful tools can be applied. The pipeline is split into 2 parts, pre-production and production. You can bring in different tools at various stages. For example, during the verify and test stage, automated static code analysis tools can be used to improve both security and efficiency. When deciding when to focus on security, the answer is simple. Do it early. The sooner you begin, the better. If development planning has already started, security should be part of it from the ground up. Starting early means it's easier to build strong security into the application and keep code consistent. If you wait too long, it gets harder to add protections later, especially if the original architecture doesn't support them easily. Delaying it may mean that you don't get the resources you need, and treating security as an afterthought can lead to weak spots in the system. Going forward, I recommend that all developers receive DevSecOps training so that they understand the security policy and how to apply it. A policy only works when it's clearly understood and actually followed. I also suggest setting up automated monitoring to catch vulnerabilities and external dependencies and add another layer of protection. To wrap things up, security should be a top priority right from the beginning. Developers need proper training both on general secure coding practices and the specifics of the organization's security policy. A good policy is only effective if it's enforced. That means there should be checks in place to make sure every deployed application follows the policy. It's just as important to keep reviewing and updating the policy so it stays relevant and effective even as the system evolves. Here is a list of the references used.